In today's lesson, we're going to continue thinking about specific versions of hypothesis tests. So a couple of lessons ago, we saw the general procedure of how a hypothesis test proceeds, and we've been looking at specific iterations of those. And in particular, for today's lecture, we're going to be looking at testing population proportions. So with today's lesson, we want to understand how we can run hypothesis tests around population proportions. Of course, there's a little typo in these learning objectives here, so I'll make sure to correct that. But we're just looking to test population proportions. And if you think back to when we looked at confidence intervals for population proportions, we saw those followed basically the same procedure, where we essentially took the normal approximation to the binomial and then used that to come up with our confidence levels. We're going to be able to do a similar thing when we're testing the hypotheses around them. So if we assume that we're taking a sample from a binomial distribution with n trials, and when we don't know what p is, and we think about testing a hypothesis that is of the form p equals p naught versus some alternative of p not equal to p naught. Of course, we can always consider the single tail alternatives. Point out the usual caveats here. The equality sign is always going to be with the null hypothesis. The alternative is defined in relation to what our null is. Well, we saw that the normal approximation, so if n and p are such that we can apply the normal approximation, then if we take the proportion and we take off what the proportion would be under the null hypothesis, and then we scale it by the estimated variance, that this is going to be approximately normally distributed and follow a standard normal distribution in particular. So if the null hypothesis is true, we can say that this is coming from normal 0, 1. And so how can we find the p-value? Well, we can do it in exactly the same way that we saw with normal hypothesis tests before, right? And so this is a process that's likely becoming somewhat familiar as we've seen it a few times over. But let's take a look at it. So we'll have our distribution here, right? And again, it's going to be approximately normally distributed. So this is our normal distribution. We calculate some value for p hat, and we'll assume right now that the p hat is above. Of course, the same thing is going to happen in reverse if it's below. But we can shade in the upper tail area. There's also going to be some negative version of it, which we can shade in on the lower portion there. And the p-value is going to be the sum of those two areas, right? And so if we say that we observe z, which in this case, we're thinking about z as being that standardized statistic here, and that's also probably what we could have labeled on this graphic, but of course it's going to ultimately be the same if you're doing the standardization or if you're not, just changes what value is going to be in the center. So if z is the standardized version, then the probability is going to be the probability that the absolute value is greater than the absolute value of what we observe, which we can break down into the sum of those two areas, right? So again, we're just thinking about drawing out that graphic, looking at which regions are going to be more extreme than what we observed, and then computing the probability associated with those regions, right? We can use tables, critical values, statistical software, any of the above. If we're looking at a single tail hypothesis test, then we simply want to exclude the tail that does not provide evidence against the null. So if the null is greater than or equal to, we just want the lower tail. If the null is less than or equal to, we only want the upper tail. So the procedure is exactly the same, right? And so if we think about what we're really doing here, is all we have to do is figure out what the sampling distribution is. And because with the binomial proportion, we saw that the sampling distribution was normal, the exact discussion that we had about testing normal populations is going to hold. In the last lesson, when we were looking at things that followed a t-distribution, as soon as you know that the sampling distribution is the t-distribution, the exact same procedure is going to apply, right? And so all that really matters is figuring out what is the distribution of this statistic so that when you want to compute those tail probabilities, you're computing them from the correct distribution. So we can use our critical values instead, right? And so you take the upper and the lower critical value, and if you're outside one of those, then you would reject the null hypothesis. And so the procedure is sort of exactly the same. So we can apply the normal approximation to the binomial distribution to run the hypothesis tests. Again, we have to consider what our alternative is to compute those p-values, but otherwise we're doing it in exactly the same way that we've already seen before. So in the next lesson, instead of looking at another specific type right now, we're going to be talking about some other features of hypothesis testing generally, and then we're going to get into slightly more complicated confidence intervals and hypothesis tests. Ultimately, they're just going to build on exactly what we've been doing over the last several lessons. So I hope to see you all in those coming lessons.